everyone, welcome to another stream. And today we are joined with Marshall. Marshall works as a DevRel at Jito Labs, and he will enlighten us today with what Jito Labs does, what are Jito Bundles, and how to send Jito Bundles. Plus, the most important thing, which everyone keeps talking about, how do you optimize those CUs while sending those transactions or constructing those transaction bodies. So I'll pass it on to you, Marshall, like to greet our audience and give a little bit brief introduction about yourself.
Right, yeah, thanks for having me. Yeah, actually, it's MEVREL. We really like to lean into that. It's one of like our big things here at Jito Labs. Yeah, so I've been at the company for about 8 months now. Work exclusively in MEVREL, is similar to DevRel, but we do a lot more technical stuff, specifically with searchers and validators. So what does Jito Labs do? They essentially provide a turbocharged Solana trading experience. And that specifically, the kind of the big use cases for that are obviously like low latency transaction sends, because you want to get your transactions in as fast as possible. And then also low latency data shreds. Those are kind of more relevant for validators. So as mentioned, outside of validators, another kind of subset of people that like to use it would be like Telegram bots. And then generally just any type of high frequency trader or high frequency searcher, since we're really focused on getting the low latency transactions in. Some of the like bigger problems that we try to address is obviously like MEV protection. So that's maximum extractable value. And as part of that, to get some of that kind of characteristics, fast transaction sending helps with that as well.
Got it. So, Marshall, I have used and have been hearing a lot about bundles, and it solves a lot of problems and introduces a lot of new functionalities as well, which is not possible with your native Solana methods or native Solana RPC methods or native architecture even. So would you like to share a little bit more or talk a little bit more about bundles, but first talk about what's the issue and why bundles was introduced into the space, or Jito bundles were introduced into the space, and what issues they address and in what way they address those issues.
Yeah, no, that's a really great question. So when the Solana market's experiencing high traffic, typically during most of the bull markets, you have the simple problem of like landing a transaction fast, and that's one single transaction. So when there's high market activity, you don't really know when it's going to land. I mean, you have some idea of a time frame, but it can take quite a long time. Which, if you're doing high frequency trading, waiting around on a price or a quote to take forever is not ideal at all. You'll likely lose quite a bit of money. Um, if you're not even trading and maybe you have some program that is dependent on time and it can miss that window, and therefore the smart contract might not be valid, or it could put things in other state. So really it's like a timing issue on that. And so what bundles came about to do was, in that case, with a single TXN, at a minimum, you'd want that transaction to be as fast as possible. And that was great. And then kind of expanding on that is, there are things that are kind of correlated that you want to state, or some type of like sequential type of atomic characteristic that would allow multiple transactions to always guarantee that they were, sequentially executed. And if one of those failed for whatever reason, then the entire set of transactions would fail, because you wouldn't want like one transaction to pass, one to fail, and then another one to pass. And then you have kind of like this, sequential state that's not working because obviously one of them failed. So bundles actually provide that, and they give you the ability to send those extremely fast and get MEV protected, so that you're not sending these transactions out of order. Some people ask that, why not just send several TXNs without using that? And that's the problem you'll run into, is in high network traffic and at other times, they can send completely out of order. And you really don't have any guarantees on what's happening.
Got it. Yeah, I mean, I really like the serialized and atomic nature of bundles because Solana transactions have a particular CU limit. You cannot exceed that limit per transaction, right? So bundles enables the users and devs like us to do multiple transactions or do a very complex job, divide that into multiple transactions, serialize that, and do that process in a series of transactions rather than having a one heavy transactions, which is not even possible if you exceed that particular cu limit per transaction.
Hmm.
And yeah, I mean, for example, we are going to see example where or examples where first, in the first example, we will see how we can execute a bundle where first, uh, in the first transaction, a wallet sends a token to another wallet, and then once that is done, then and then only the second wallet will send another token to the first wallet. So I think this is not possible without bundle. I mean, some might argue that you can have a program in between which keeps track of this, but bundles just make it very simple and guarantees for both the transactions to land in same block. Am I
Hmm.
right, Marshall? Yeah.
Yep.
So yeah, that's really cool, and that's really new set of opportunities and possibilities bundles open up for everyone. So I just quickly wanted to mention that I earlier mentioned that bundles are not something native to the Solana infrastructure or Solana uh, functionalities, right? A normal Solana validator cannot process a bundle or cannot process a bundle transaction, right? So that is why at QuickNode we have developed this add-on, which is available via QuickNode Marketplace. As I mentioned, it's not available via the native RPC method, so that is why it's available via Marketplace as an add-on. So once you have this add-on installed on your RPC or RPC endpoint, on Solana, on QuickNode, what you can do is you can simulate bundles, you can send bundles using your QuickNode RPC endpoint itself. You do not have to worry about getting another API, or you do not have to worry about managing multiple keys, managing multiple APIs. So, Marshall, if you don't mind, I would like to show everyone or our viewers an example of bundles or an example of what are the possibilities using bundle.
Yeah. Let's
So,
dive into it.
so I have this example where what we will be doing is, or what we will be seeing is, uh, the the example which we talked about earlier, where a wallet sends some token to another wallet, and if and only if that transaction is completed, the second transaction will take place, where the second wallet will send some tokens to the first wallet. So in this case, we are calling them wallet A and B, and yeah, over here we have some basic imports. We are importing a bunch of modules from Solana Web3.js as well as Solana SPL token library, because obviously we will be working with SPL tokens, in this case USDC and Bonk tokens. So that is why we need some modules from the SPL token library. For example, this one, get or create associated token account, which we will use to check if the associated token account for both the tokens exist on both wallet addresses or not. And if not, we will create them. Then we will create SPL token transfer instruction using this module. Then we will also need base 58 to encode transactions. So that is why we are importing this library and or have installed this library. And then we have a file system library to access all the secret key files, which we have over here. The secret key for wallet A, secret key for wallet B. But I would highly discourage having your secret keys or private keys or secret wallet secrets stored like this in a file system if you are going to upload it to GitHub or any other code sharing platform. Always use your secret or private key in that particular session, and do not have them stored in any of the files, even locally. So over here we have a bunch of constants. First is our QuickNode endpoint, which we will use to send our bundle and also simulate our bundle before actually sending it. So I'll quickly grab a QuickNode endpoint from the dashboard. So I'll copy this. And then I have a constant which holds the Jito tip, which will go to the Jito tip program accounts who help us process and execute those bundles. Then we have a flag for simulate only simulate only bundle, which will make sure that we are simulating the transaction or bundle transaction before actually sending it, so that we don't lose actual funds. So if this is set true, we will just simulate the bundle sending process, and if it's set false, it will actually our script will actually send the bundle. Then we have few constants for our polling mechanism, because once we send the bundle, we will check for the validity of the bundle. We will check if the bundle has actually been sent, and if it has landed or not. Landed meaning if it has been confirmed and fully executed or not. So for that, we have poll intervals and poll timeout constants. And then finally, we have our mint account addresses for USDC and Bonk tokens. Then we have three interfaces, actually four interfaces to handle wallet secret, transaction encoding, bundle response handling, and bundle status response handling, which we will be polling for. Then we have this function to get the decimal numbers for each of these tokens. And once we have that, we have a function called create transfer transaction, which creates the transaction body for each of the transactions. So we will have connection, mint address, amount, from wallet to address, and jitter tip. So the thing with jitter tip is jitter tip needs to be added to the last transaction of your bundle sequence or the sequence of transaction. So let's say that you are sending four transactions in a bundle, then the fourth transaction of that bundle needs to be sent with a jitter tip. And in this case, we are just sending two transactions. So the second transaction will have the jitter tip account instruction. And then we have this constant source account, which will store the associated account addresses for wallet A, which we will get using this function. If they does not exist, it will create one. And the same for the destination account, which will be wallet B in the first transaction and wallet A in the second transaction. Then this decimals are stored in this, adjusted amount based on decimals stored in this. Then the transaction will be initialized using this. And this is how our actual transaction with all the instructions will look like. And if we are sending Jito tip, then this is how it will look like. So as you can see, what we are doing is we are sending the tip from the fee payer account to the Jito tip program account. And this will be the Jito tip amount, which we explicitly defined over here as a constant. And then we are getting the Jito tip account using this function. So Marshall, how many Jito tip accounts do we have right now in the ecosystem?
For mainnet, I believe there's 8. And
Okay.
testnet, I think there is 4. One other
Oh,
thing too, when doing tips, and you don't always have to do this, but it's kind of a best practice, is to always pick a random tip account.
okay.
This more relevant for people doing like stuff that is very dependent when accounts get locked. But if you're just doing trivial stuff, then it doesn't really matter.
Definitely. And that is what we are doing in our function as well. We are just picking up a random account and not, uh, you know, not mentioning a hard code, like not mentioning a particular account or not hard coding a particular program account for sending tip. It's
Mhm.
so that's a really good tip, Marshall, no pun intended.
And
And
I was going to say also too, some people will hard code it because those accounts haven't changed. So there's a lot of options
okay,
there,
got it.
just for when you're going back through that. However you want to put that in there.
Yeah, but I'll take your advice because it's coming from a Mavrel. So I'll usually always use a
Yeah,
random account from the list of accounts.
I usually say like the best option there is you can like hard code them in and then pick a random one from that set. That way you're not making one less call and waiting around in case it got stuck for whatever reason.
Got it. So over in this case, what we are doing is we are sending this custom get tip accounts RPC requests to our QuickNode endpoint, and this is one of the custom methods which gets enabled if a user or if anyone has this add-on enabled on their QuickNode endpoint or account. So this is one of the RPC and RPC method using which you can get a set or a list of tip accounts whom you can send your tip to. And then we are encoding the transactions in 64 for transaction simulation and 58 for actually sending the transaction. Then we have a function for simulating the transaction where we will be using the simulate bundle RPC method, which is another custom RPC method which gets enabled via the add-on. Then we actually send the bundle using this function. I mean, over here, we are not sending the bundle, but we are just creating helper functions, which will go into our main function and called whenever required. And the send bundle function uses the send bundle RPC method, which is again another custom RPC method enabled via the add-on. And then we poll the bundle status once it's sent to check if it has landed or not, if it was valid, and then if it has landed or not. And that we check using get in flight bundle statuses, where you can check any bundle's status while it is being executed or before it is being executed once it's sent. And we have a bunch of conditional statements over here where if it's landed then it will return true, if it's not we will throw some error or log some error. Then finally we have our main function where we load our wallets, we load our RPC URL, then we throw a bunch of messaging on terminal, then we fetch account, like fetch the tip accounts, then we fetch the resend block because that's required always to send a transaction on Solana, because to maintain the transaction validity, uh, sorry, to maintain the transaction validity. Then we have the token amounts hard coded over here. We will be sending USDC1 from wallet A to wallet B and 1000 bong from wallet B to wallet A once the first transaction is completed. Then we are constructing both the transactions over here and getting the block hash and transaction signatures. So we are setting both the wallets with block hash and transaction signatures over here and creating a transactions array and then running a for loop for those transaction arrays where first USDC transaction will be executed and then Bong transaction will be executed. And then we are simulating the transaction. And after that, we are finally sending the transaction, I mean, the bundle transaction. And after that, we will poll if the bundle has landed or not. Once it lands, we will print the bundle ID with the link to the Jito Explorer. And then we are finally calling our main function. So what do you think, Marshall? Should we run this?
I think, yeah, we should run it, see how it goes.
Yeah, I forgot. I should not be using this, I guess. Or maybe it's better if I use terminal. Yeah.
Yeah, whichever.
All right. So as you can see, both the transactions were created and tip accounts were added, tip were added, and the simulation was successful. Okay. So Now to actually send our transaction, we will set this flag as false and send it through. Okay, bundle status invalid. Why is that? Oh, okay.
Yep. That's what I was gonna mention. Like when you first send, and if you have like really good timing and you like co-located, the first ping you're gonna get back, or the response I should say, is gonna be an invalid. So then you basically have to keep going on invalids until you get a pending, and pending's the flag that lets you know, like, yes, the system has got it. And then once you hit pending, you either need to get a failed or a landed, or you can slide past that and then it ejects from the system, and then you're back onto the invalid window.
Got it. Got it.
And
So
that's
that
also depending on
explains.
when you pull. So if you pull too late and you slide outside of that small window, all those conditionals might fall apart. So,
But good thing is it finally landed.
mhm.
Yep. So let me check this URL. So we can actually see what happened
Oh yeah,
with
and
the
that's the
bundle.
other thing too. And I know it's in the guide. Sometimes it does take a while for the bundle to persist on the Explorer, since that one's also
Yeah.
not real time. So,
Yeah. Yeah. I know. I faced that. I think day before yesterday while I was working on the script,
yeah,
I- and I sent multiple bundles because I thought something was wrong, and then all of them showed up.
yep, yeah. It can be frustrating. It's really, you'll tend to notice it during high congestion a lot.
Yeah. Okay. So all right. So this is how the bundle will look like on Jito Explorer, and you can clearly see the included transactions over here. These were the two included transactions. In the first transaction, we transferred uh, one USDC from this wallet to this wallet. In the second transaction, we transferred 1,000 BONG from the second wallet, wallet B, to wallet A. So both of these transactions were executed sequentially, and the entire bundle was executed atomically, which means that if the transaction number one, which is this transaction, would have failed, this transaction, which is the transaction number two, would have failed as well. Yeah, Marshall, I just wanted to show this example to our viewers. And would you like to add something to this, or would you like to show something to our viewers?
I think that shows how everything's kind of sequential and in order. I was going to actually show another example, kind of showing you can dive in and attempt to optimize some CUs. If you want to take a look
Mhm.
at that example.
Oh, 100%, 100%. Let's do that.
All right, cool. Let's dive into it. This program primarily mocks what you'll see on the QuickNode guide. So all these imports are very familiar. You actually see that in the guide when you go to do the example, the little Jito example. And so nothing really is new in here besides the or the set compute limits, which is down here, and we'll talk about that here in a second. But the rest of these should be very familiar. Essentially, what they're doing here is we're obviously creating a transaction, and then we're going to use the memo program inside of here. And so with that, you would need the memo program imported. As mentioned in the prior example too, we got to bring in our keys because we will be signing and sending a tip as part of that. So best practice as mentioned, typically not the best to keep your secret key inside of the repo itself. And you don't want to do that in case you're checking in stuff to Git. There's several options for that. I typically recommend running it through an environment variable, but it's kind of per your discretion. Just at a bare minimum, typically not putting these in the same repo or uploading them with Git or having them in the clear where it is quite literally like your private key. Um, so moving downward, so you're going to need to set a minimum fee. Right now it's 1,000 land ports. Sometimes that always doesn't land fastest because that's the bare minimum. But for what we're doing now, which is fairly trivial memo transaction, it should land relatively quick. And if not, we can go back and tune it. As mentioned, since we're using a memo program, we want to show kind of how you can expand a bundle and create 5 transactions. So we're going to set that to 5, obviously. As mentioned in the other video too, we're going to sim this before. And so I should probably set this to true, just in case you run into any errors.
Yeah.
So once you have your endpoint set up through QuickNode, and you set that up through the dashboard, we're going to pull on this bundle so that we can ensure that it actually gracefully landed and it's on chain. Because just sending it is always possible, but we also need to make sure that it, gracefully landed. So kind of going back through the same type of interfaces that you saw in the guide in the prior program, these are going to help us essentially get our responses back from the server and each of the types. I think one of the bigger ones that you probably want to see would be the Little Jit add-on, which allows you to actually now talk into some of these RPCs. We have Git regions. So yeah, from here, these are the similar RPC messages that you saw in the prior example, and nothing new there. Scrolling down here, same similar setups, all of our helper functions, and things that we've kind of appended in here and made them a little bit more verbose is the validate simulation. So what we've done
Mhm.
here with validate simulation is it's very much what you would see if you look at the system program in SoulScan. Essentially, once we send a bundle and we're looking to kind of optimize our CUs, we need to get a response back. And so what we'll do then is get the response back and parse it back, essentially as you'd see all the fields when you look at any type of transaction explorer. So this is quite literally doing that. Per the number of indexes we send, we essentially bring that back and deserialize them to show essentially the logs and the states within those. And we're going to do an example on this so you'll be able to see this and compare.
Mhm.
And then we do kind of a little kind of trivial metrics just to see like our total uh, compute units, and then the average, just so you can see kind of how we're optimizing stuff down to get down to much better numbers when we start off from this final one. Okay, and so now we will step down into very similar, creating a transaction again. Again, this one though, we're going to be using the memo program. And so diving down into this, here we'll create the transaction, very similar to like you see in the prior example. You might notice a couple different fields here, but we'll talk about those in a bit. And we'll also talk about this comment or block here in just a minute too. But we'll get down to kind of like where the optimizations and where the actual computes being like happening. Specifically here with the memo, we are obviously encoding a string. This is a very kind of trivial string, and it's essentially just outputting, this is the index 0 through 4 because we're parsing through 5 TXNs, and it's going to append each of those memos into each TXN. So if you can imagine 5 TXNs, each with a memo, and then as mentioned in the prior video, we want to add a tip to that. So the final TXN will then include the minimum tip, which you have to put on there to send into the block engine. So again, nothing new there. And then obviously we will sign it. Get tip accounts, nothing new here. We saw that in the prior example. Those are just getting your mainnet tip accounts from the RPC. And then now we go into a very similar helper that we saw in the prior example, which is pull bundle status. Nothing new here. This is just allowing us to confirm that bundle that we sent into the block engine. During high congestion loads, you might have to change some of the timeout polling intervals because things may take a little bit longer than expected, especially if you're doing the minimum tip. And if you miss the window to confirm, you can always go on the block engine and look up the bundle ID, which we'll show here in a minute too. So again, nothing new going through the polling statuses. Kind of we'll step back into main function here. So with main function, we're going back again to very simple cosmetics that you need to kind of do any transaction. We're going to get the wallet that we need to sign and the funds allocated with that account. Then we also need to get our endpoint from QuickNode, and then also the the add-ons for those for the RPCs. Once we have a connection into there, then we need to start getting the tip accounts so that we can tip on that last transaction. So as expected, we're going to get the tip accounts. We need to then get the recent block hash, which is also very valuable when sending through the block engine, which you can again get through the RPCs. And then we will dive kind of into the construction of that transaction. As mentioned, we're going to do up to 5. So we need to iterate through there and create essentially each one of those transactions, each containing the index plus 1. So we will get 5 when we go to look at how it's actually deserialized on the Explorer. And then for each of those, we need to sign. And then on the very last one, as mentioned, we need to add a tip amount to that. And for the final encoding, then we essentially encode these into base 64. And after you've added the Jito tip, you step down in and sign the transaction, and in base 64 encode it. And then we encode it back to base 58 so we can properly send the correct format into the block engine itself via send bundle. So after you've encoded the transaction as expected, we want to simulate the bundle. And this becomes really useful when you want to optimize CU because it'll essentially give you the consumed compute units from the block engine or the validator itself so that you can begin like tuning them. And so you need at least some way to, sanity check what numbers you expect and be able to lower that CU. Because if you're constantly just sending transactions without simulating them, then you're kind of paying a cost quite literally for that. So having the simulate bundle RPC is really, really useful. It's very often used for people to simulate all different kinds of things. And it's a tool that is like, it's very useful at a minimum, but it'll help you tune this. And it's the only possible way you can do this without just kind of guessing and looking at SolScan or whatever program log you might be using. And as mentioned before, when we do this sim, I'm going to recall the validate simulation method so that way we can get like the full verbose output that looks very similar to what you'll see in SolScan. And that way you can kind of begin learning how to fish by optimizing the CUs. And then as we have everything set up to send away, and so what we'll do then is we bundle up all of our transactions, and they're all encoded, signed, recent block hash, and we know where we're going, and then we send them off via send bundle. And after we send them off, we need to ensure that we also poll to ensure that it lands on chain. So again, depending on the network state, you might have to change these to be a little bit higher, but for our purposes, they should work as expected. So, all right, I think that's it. Should I go ahead and run it now and show folks? So now we'll go ahead and run that example.
Okay, simulation went through.
Yep. So yep, simulation went through as expected. And as you can see here, some of the stuff to kind of, as we start diving through, and then we'll do a final diff on this to see how much you've optimized. So the total computes used on this one is about 50,440. And we can zoom back up here and you can see each of these transactions with stuff as we expected. The indexes gives the length. And probably the most important thing to note here is on this last one, you see this last kind of tip program, which adds an additional amount of CU. So obviously we know it can sim. So let's go back and change this to not sim so that we can go see this live on chain. False. And recall this is what we use because now it won't tell us, but we can go see and do manual math on SolScan. All right, now we can go, let's see where it opens this. So after you open that link and you dive into the bundle, kind of the stuff that we've expected from looking at that output, you see the 5 transactions here, and each of them containing essentially a memo. And we'll go over to SolScan here real quick and look at the verbose output that should look very similar to like a system log.
Mm-hmm.
Okay, and so, yep, as you see, some of the stuff that looks very familiar, this is kind of the instruction data you'd see with our string. And as you scroll down, you'll notice that this looks very similar to what we did with the output, where we actually now see what the instruction is that's serialized. And more importantly, for optimizing CUs, we see this. We see roughly about 10,000 CUs of 200,000 compute units. And so this is what's actually set by default. So if you're not essentially modifying these or reducing the limit, you're essentially going to get the max requested every time. And that's relevant if you want to optimize your CUs because you want to essentially cut down the amount you requested so that you can get essentially scheduled quicker because you're not getting like a buffer that's essentially giving you way more than you need. So you're optimizing what you request. Uh, and we'll show that here right now. All right, so we'll do, yeah, so, all right, now, sorry. So to optimize the CU, first we want to then go back to the way we learned how to fish and essentially set this back to true. This will allow us to simulate and recall that our prior one was, I think it was 50,000 CU. And so we'll
Yep.
go down into where we serialize the data. And so this is where you kind of got to start thinking of like, what are these instructions doing? What is the compute required? And what type of work are they doing internally within the transaction? And so one thing that sticks out a lot to us is that a memo is quite literally serializing the string. And so we
Yep.
know that there's some type of operation involved in the number of characters here. So as kind of a sanity check here, why don't we just only serialize kind of the more pertinent data here, which is just the index. So we'll take out all these ASCII characters and we'll essentially only serialize the memo as just the index. And we'll run that and we'll see, if we're doing less serialization per transaction, ideally there should be much less compute units. So we'll run this again. Okay, so after we've ran that and we see that we've gone from 50 KCUs down to roughly 9,765, we'll go back up here and we'll look at how many compute units we actually use. So on the very last transaction that includes the memo and the tip, it's 2,073. And on any other prior transaction, we're only using 1923. So we go
Okay.
back up in these variables that I had mentioned, and we'll just set this to, we can do 1950, just because, again, you want to err on the side of caution, typically pad a little more. So that way, if you're interacting with programs that might do a slightly different CU consume, depending on what's going on, you're always at least ideally landing that. You typically don't want to optimize so far that you run the risk of it failing. And we know that the tip transaction is always 150, so we'll leave it at that. We'll save that and we will go ahead and run this again. All right. Now we're ready to actually simulate this since we've confirmed that we are no longer requesting 200,000. We're only requesting the minimum amount. We'll go ahead and run this and see how it lands.
Okay.
Fine.
Okay. Let's
Okay.
go.
Perfect. Okay, so now we can see that it obviously landed. Much of what you would expect. We have the 5 transactions. Now let's dive into what we saw in some of our simulation logs so we can kind of sanity check that we didn't just print stuff that wasn't maybe necessarily happening. So
Mm-hmm.
as you can see, we dove back in. Here's one of our transactions. Look, we set 1,950 like we saw in the variable. And then when we go down here, more importantly, you can see from the system logs that we are only requesting 1773 of 1,800. So what that is doing is, compared to the 200,000, is we're optimizing the compute units that we request. And this is ideal for when you set fees because you don't want to set higher fees than you need to, which is essentially paying more than what you would take in profit ideally. So minimizing down the compute units is actually helping your program not only run more efficiently, but in terms of scheduling, you're not requesting like the maximum amount like other programs does. So it gives you more better opportunity to get scheduled. Um, and so now you're probably wondering, well, that's pretty cool. We've reduced this almost, I don't know, from 50K down to 10K CU. Can we do any better? And the question is, or the answer to that is yes, we can. So in this example, recall that when I mentioned how you kind of how you learn to fish when optimizing CUs is so that we know
Mhm.
that within each of these, there's essentially some type of compute being done, and we're literally encoding a memo, which is some type of string. So zooming out, you'd have to think, well, wouldn't it be a little bit more efficient if I'm trying to optimize stuff to compress down these indexes into just one transaction and keep the ASCII keys there where I'm doing 0 through 5 and just compress it? And that's what we're going to do. So going back to this example, we can see that very similar to the prior one, we're essentially everything's the same. What we've changed here is we're quite literally doing the indexes as 0, 1, 2, 3, and 4 with spaces just because we can. And we will go ahead and run this again. And remember, some of the tooling that we use is very similar. We're still doing the same amount of compute units, as you can see up here, and we always have to add the 150 for the tip. But since we only have one transaction, it'll quite literally be in this transaction itself. So let's just go ahead and see how this runs. Make sure I said simulate, but I think this one dumps no matter what because I don't have it in the block. But let me check. This is set to false. It doesn't matter. So, okay. So yeah, now we can go ahead and run it. And there you go. Now we're down to half of what we had before, which is 4,943 CUs, as opposed to our prior one, which is roughly about 10,000. And you can
Yep.
see now we have this one transaction. We use 473, 150, which is just the tip. And you can verify this because here is the memo quite literally. And there is the tip on the end. And then we can see that it simulated successfully, and we can go ahead and now send this. I think yep, it's already sent, so we can go ahead and check it. Wonderful. So here we can see our bundle landed, and we can go ahead and dive in on SoulScan, verify everything we saw in those logs was not, made up. Verify our compute units here. We can go down and obviously see the memo right there. And then the one that looks very similar to the output is right here. So 4,643 as opposed to the prior 10,000. So this is a way, again, kind of summarizing is when you understand the operations within the instructions, you have to understand quite literally the ordering and then ways you can kind of like minimize these or compress them so that you're not overflowing per instructions. So you can begin to start diving into each of those and really understanding like what calls they're doing, using simulate bundle to then sanity check what you'd expect is getting consumed. And then you can go through and optimize those. And essentially you just iterate through and test them and get to a point where you have a good padding that you can use for a given set of transactions or a bundle. And you can use that and optimize your CUs. And that will ideally give you the best possible way to land with your scheduler. And then you can use some of the tipping APIs to get you the best possible tip for that instruction set.
Got it. Yeah, I mean, man, this was very insightful, and I think it will help a lot of people around think around how they can think differently and move few things around to optimize CUs.
Hmm.
Hmm.
Yep. And that's literally kind of how it goes. A lot of people will run these on against MLs or whatever model they're training, um, more sophisticated ones, because on other programs or you're in different markets, they use different consume rates per whatever the market's doing, and so you always have this like fluctuation. But those models are trained to know like where the market's at, and they'll actually pull like the best CUs for that time, and then they just call to an API to do like the best tip per that per the percentile with whatever the ML tells them. And so that's more like the sophisticated folks that do that. But you can still run something maybe not as like detailed as that, and you can kind of cache stuff locally, especially for like a memo program like we did. You could quite literally cache this and just know per character what you're doing.
Yeah. Yep. 100% agree with you.
Cool. So when we 50x to 5K, I'll take it. 10x. We 10x. They love that, and we 10x engineered quite literally. I love it.
All right. So thank you so much, Marshall, for enlightening us and teaching us like how we can optimize CUs and actually make our transactions cheaper. So thank you so much for doing that. And I bet this will be very helpful and very insightful for our viewers who are watching us and wants to do a lot of Solana development. So yeah. So thank you so much again for joining us, and for our viewers who are watching us live. If you have any comments or if you have any questions, feel free to drop them in the chat, and we will reply them in the chat. And for people who are watching us on YouTube after the live has ended, you can drop the comments in the YouTube comment section, and we will go through each one of them and answer them.
So Marshall, thanks for having me too.
All right. Any closing notes you want to tell to, or you want to convey to our viewers?
No, just get there, and the best thing I can recommend with this stuff is just practicing and using the tools you have. I think that's the best approach on here, and just iterating through. And once you start learning some of the fundamentals, you'll be amazed at how much you can apply those and kind of optimize all your transactions. So
very well said, sir. So on that note, thank you so much everyone for joining us, and Marshall especially for joining us and doing this with us. So see you all in the next one, and hopefully Marshall, we get to do this sometime in future too. Another one.
Looking forward to it.
All right. See ya.
Bye.